All right. So my PhD student Liang Shen developed another criterion for region growing based on the human visual system. We mentioned earlier that in the human visual system we have certain thresholds for detection based on contrast, and one of them is the criterion of GIAN, or just noticeable difference. And we express that as LCT, where CT is a threshold contrast and L is the background luminance. Like CT could be 2%, 0.02. That's the threshold of perception. So using that, we can say CT is proportional to 1 over L to the power of 0.5 or 1 over square root L. This is related to what is called the Rose-de Vries region, where CT decreases when the background luminance increases, and there is a curve here. The Weber region is where this threshold is approximately constant for various increasing levels of background luminance. But before that, there is the Rose-de Vries region, in which the threshold increases as the background luminance decreases. So there is this region where there is a variation in the threshold contrast, and after this threshold, the Weber region starts where the threshold is approximately 0.02. So the Weber region CT is independent of the background, and CT can be written as JND over L, C naught or constant. But in the other region, we have CT proportional to 1 over L to the power of 0.5. So it is possible to determine JND as a function of the background gray level from psychophysical experiments. So we conducted a test where we set up various patterns of foreground and background levels using square boxes and line patterns. So pixel width ranging from some 1 pixel to 16 pixels and spacing of 7 pixels and vertical bars like this. This was one of the test patterns, and the background and the value of the foreground, they were changed, and some tests were conducted, and the threshold of perception, the just noticeable difference, was mapped to be like that, which is approximately that, the Weber-Fechner relationship. Now this was just based on one experiment with one person, so it needs to be averaged over multiple observations by multiple people, then you will get a curve close to that. But we could get a similar curve using test patterns of this nature. What is the smallest object you can detect when the contrast is varied? And these are the line pairs, the gratings. What is the finest grating you can resolve before it just becomes blurry when the value of this and this values are changed? This is one illustration. So the JND condition was defined as P1 minus P2 less than minimum of JND P1 and JND P2, where P1, P2 are two connected pixels. So instead of just taking the pixel value difference, we are taking the contrast value related to that as the difference. So we call this a region growing criterion based on the human visual system. This was followed by removal of small regions by merging when a connected region with the minimum mean gray level difference. Then merging was performed if any two neighboring regions meet the JND condition, with P1, P2 representing the means of those regions. And it was iterated. So we got these results with those same test patterns with various levels of noise, that these are the two objects of interest, black and white, at different levels of noise in the upper part and lower part. And the requirement was that both of these objects should be detected in both of these at different noise levels. And we saw that it worked well. And then we extended to detection of calcifications by multi-tolerance region growing. As I mentioned earlier, calcifications, there could be many of them, and we need to analyze the shape characteristics and size characteristics of each one and get a map of how these shape and size vary in a cluster. In the case of homogeneous, or rather in the case of benign calcifications, most of them are fairly round and smooth, and there are not many of them. Whereas in the case of malignant calcifications related to breast cancer, there are many of them in a given area, and their shape characteristics vary. There is heterogeneity in density, whereas the benign ones are more homogeneous and smooth in shape. So Shen did his MSc and PhD related to these problems, and the calcification detection algorithm starts with a selection of seed pixels, the detection of potential calcification regions, and then confirmation of calcification regions. So that procedure, I'll go through that. Selection of seed pixels. Calcifications, because of calcium, they are of higher density and hence appear bright on mammograms compared to other breast tissues. So every pixel with a value greater than the median gray level of the mammogram is identified as a potential seed pixel. And then there are some additional conditions to reject regions that could not possibly be calcifications. Then these pixels are processed in sequence by selecting the highest intensity. We don't take them at random, but at the highest, start with the brightest pixels, and then grow regions, and repeat region growing as long as one of these pixels has not already been included in a region. So detection of potential calcification regions. So the region growing algorithm for this application, we made a small modification. Every 4 connected neighbor FMN of the pixels belonging to the region is checked. First there is a seed, so check its neighbors, and those that are included check their neighbors, and so on, iteratively until region growing stops. The criterion to include the new pixel must be between these limits, 0.5 times 1 plus minus tau or 1 minus tau times R max plus R min. These are the current maximum minimum of the region being grown. So as the region grows, these values get updated. The tau value was modified, that is multi-tolerance, from 0.01 to 0.4, and the step size was related to the inverse of the seed pixel value. And then for each region that was grown for a given tolerance, a feature vector was computed. As I mentioned earlier, multi-region growing for the same object, and then you select the best. So compactness, C equal to 1 minus 4 pi area over perimeter square. Compactness is typically defined as perimeter square over area, but this normalizes the value 0 to 1. And then XY coordinates of the centroid or center of mass of the region. Size or area in number of pixels. So this is the feature vector that I had mentioned earlier. So for each of the thresholds, we get a different region, compute the feature vector, compare the feature vectors one step to the next, and then choose the one where the difference is minimum. That is, the region is sort of stabilized. The normalized distance between the feature vectors for successive tolerance levels, the regions obtained by successive tolerance levels, is computed. The feature set with the minimum distance is selected as the final set. And that is still a potential calcification region. To confirm if it is calcification or not, we put a limit on the size 5 to 2500 pixels. The pixel resolution in our digitized images was 50 micrometers per pixel. So this corresponds to 6.25 millimeters square, fairly small microcalcifications. The upper limit, that is. Calcification can't be that big. Condition on contrast must be greater than 0.2 of that calcification region because it has to be brighter than the background. So here are some benign calcifications. This is just a small portion, 512 by 512 pixels, 2.25 centimeters. Out of a full mammogram, that is, 20 by 25 centimeters, 200 by 250 millimeters. So it's a small fraction of that. The full image was 1536 times 4096 pixels. I hope you can see the boundaries obtained. So the boundaries obtained are marked here. So all of them have been detected reasonably well. This calcification, it didn't catch that incursion there. That appears like two calcifications, maybe multiple calcifications grouped, or one with varying density. I can't say. This is a malignant case with many, many calcifications, and these are all the regions detected. It's a little difficult to analyze images of this nature, and our colleague from radiology, Dr. Desertel, when we showed this, he said, well, he actually counted how many are there, and we checked how many we detected. But then he said, well, if there are 200 calcifications, you don't have to detect 200. If you detect 180 and say there are so many, that's enough to make a diagnosis that it is malignant. If you miss one or two, it doesn't matter. Of course, if you don't detect half of them, there's a problem. But if you miss 10% of these, there is no issue, because it's still above the threshold of diagnosis of malignancy, the how many calcifications per centimeter square or something like that. But the boundary is important. Look at all these boundaries. They are matching fairly closely to the original boundaries, and that was also checked by the radiologist. And then we computed shape factors using these boundaries. Shape analysis is the next chapter. So we wanted these contours to match the shapes well, so that we can compute accurate shape factors for their classification. We will see that in the next chapter. This is just segmentation. So we counted all these and then gave some measures of accuracy. I won't go through all of that. They are in our papers and in the book. My collaborators in Spain, Carmen Serrano and Begonia Acha, they developed another technique. One of my students, Gopi Kurduvalli, had developed two-dimensional linear prediction algorithms for data compression. In linear prediction, in, for example, speech processing, linear prediction is done using a block, a sliding block, using the data values in this block, try to predict the next pixel as a linear combination. Take a linear combination of the pixels in a reference window, predict the next value using appropriate coefficients, which you find by optimization. And then compute the prediction error, because you have the next value really, and track the error. If the signal is stationary, then the error will be low, and when the signal changes, like when I say, for example, asterisk or asterisk, as one says first you have a vowel, then you have a fricative, then t is a plosive, and the characteristics change, and the model doesn't predict these anymore. So you break the model. So you found a breakpoint. So tracking the linear prediction error can help in identifying changes that are marking points of non-stationarity or a different process generating the signal. The same speech, but a vowel versus a fricative, voiced versus unvoiced or plosive signals. So you mark the boundaries and you segment the signal. That's commonly done in speech signal processing. You can do it with heart sounds also. And you have examples in my other book on biomedical signal analysis. For 2D, there are two-dimensional prediction algorithms where the reference is not a series, but a block of pixels. What should that block be is another question. Do you want causality or not? So rectangle, square, or symmetric or not, and causal or not. So there are some considerations. But anyway, two-dimensional prediction is established, and there too you can track the error. So you start from somewhere, and using the data, you build your linear prediction model, apply it here, and find the error, or let's go here, find the error, and then the error is very small, and when you come here, the error increases because that cannot predict this. And then you say, okay, there is something different. Mark that. So for calcifications, we did the same thing. This is a part of a mammogram. Mammograms are fairly fuzzy and smooth. There are ligaments and ducts and so on, but there could also be parts like this. So if you take this portion and then predict the next pixel, there is good prediction after the model has been learned. And then as you slide the box of prediction, the model cannot predict that anymore, calcification, so the error goes up. And then you say, I found something that is different. Mark that. So all these black pixels are points where the prediction error increased. Okay. So look at these calcifications. There are a few others there. That's a duct, I suppose. But these are calcifications. But even here, for this duct and something here, you got prediction error crossing the limit. And then for each one of them, you grow a region using one of these region growing criteria. And these are the regions obtained. And then, of course, you reject regions. For these, regions were grown, but they were rejected. But they are not calcification. You check the density. You grow a region, check the density inside. If it is not above some threshold, you say, no, it cannot be a calcification. Or if it goes like that, that cannot be a calcification. So this is the final result, where most of these have been detected, and we have published the accuracy of detection and such statistics. I won't go through that. Okay? So detection of potential seed pixels. What are you asking about? Seed pixels? You were asking about how to detect seed pixels. One is you can take every pixel, but that's a waste. You can take every pixel that is above a threshold, but there are some others that could pass. And this way, it is a little better. You are looking for discontinuities based on prediction, and you are getting a better collection of seed pixels for calcifications only. And then there are some problems here. The prediction failed. There could be mammograms that are more complex than this. This is very smooth. Yeah, this is what I said. There is a duct or ligament or something there, some fibroglandular tissue. But when you grow regions here, they don't meet the subsequent conditions for calcifications which I described earlier. They get rejected later. At the first stage of detection of something, you must always allow more false positives and have high sensitivity. You want all of the calcifications detected in the first stage and marked, even if there are many false positives. And then you reject the false positives later by more criteria, by adding more conditions. But if you miss something here now, you cannot find them again later. You don't have any more steps to detect them. So our initial steps in all of our algorithms always allow false positives, and then you get rid of them. Okay.
I think I was asking the accuracy and other measures. Something like ground truth is there, detection algorithm is there. So when we find the accuracy and measures, we go for a pixel level kind of. So pixel level, is that required that much accuracy, or from the medical perspective, if it is detected, it's okay kind of like?
Yeah, how do you measure the accuracy of detection is the question. We have counted the number of calcifications. Dr. Deserter looked at it. He said, well, we don't do it in diagnosis, right? He doesn't, in the clinic, he doesn't sit and count calcifications. And each time you count, it is a different number. It's very hard to count in these images. So in some cases, we said it is 200 plus minus 10. Each time you count, it is 195 or 205 or something. It's very difficult. And that is not done in practice. So the final question is, you go through the whole process and do the shape analysis and classify, and then at the end you say this is malignant, this patient has cancer. If that is correct, you are done. If they got, as I said, 200 calcifications and you detect 190, that's good enough. If you get 205, okay, you're not calling it 1,000 or 20. So there are different measures. If you want to measure exactly the difference between what is detected and what is the ground truth marked by the radiologist, we don't do that for calcifications. We have done that for tumors, breast boundary. I'll show you that later, where the radiologist has drawn the pectoral muscle, the breast boundary, the tumor boundary. There we can measure distance and various measures. I'll discuss them later. For calcifications, there is no need to check the shape of everyone because even the radiologist cannot draw that.
The deep learning era, we compete for such kind of...
Yeah, so one needs to take the larger view and say, what is the final goal of all of this analysis and where do you want to compute the error? The shape here, with the calcifications, it is nearly impossible to get good ground truth. And if I get one radiologist to draw all these contours, which Dr. Desitels did for tumors, and we publish, the reviewers say, well, you got only one radiologist. Now tell me, who has 100 radiologists sitting to draw the contours? Nobody has. In the whole wide world, nobody has 100 radiologists who will draw the contours, and then they will ask you, make each radiologist draw the same contour 10 times. It's not practically feasible. So these reviewers come from some other planet. So we have to, at some point, say, no, this is not feasible, because that is not what is done in practice. We have to find other means of evaluating the validity of the results. Reviewers have told us these things. I'm not joking. Any other? We are changing the topic slightly here. Any other comments, questions?
I just need to add to what Sir was saying. So I had an instance where I happened to give it to two radiologists. Okay. So one was from over there and another one from Africa. So, but they disagreed on the instances. So what they suggested was like, give it to another third radiologist. Mm-hmm. So that fellow came back with an entirely different bounding process.
Yeah.
So now I don't know what to do now. So which one is which? So in such a case, like, how do we address this?
Yeah. As engineers and scientists, we can take a different view. We can say, well, I detected this contour and this radiologist gave me that contour. There are measures to compute the distance. I'll show some later on. Mean distance to closest point, or house dot distance, and so on. You measure them and say, okay, my deviation from radiologist 1 is something. The agreement is 95%. Another radiologist draws a different contour. My agreement is 93%. And another radiologist, I get 93%. Okay, fine. What is the difference between these two radiologists and this radiologist and that, and find, and that may be 80% agreement. So my agreement, my segmentation is agreeing with each radiologist more than their own agreement. Then I can say I'm better. So the inter-radiologist deviation is one. The deviation between the computed result, whichever way it works, you argue as you wish. Okay? The other thing is, of course, to take the average of the contours drawn by the radiologist and get one distance measure. But if they are very different, then the average may be not meaningful. Okay. With my collaborator, Denise Gugliato in Brazil, we did some work on fuzzy segmentation. She is a computer scientist and I'm an engineer. Our languages are a bit different. But it was interesting, and we applied it to the segmentation of breast tumors in mammograms. That was our focus at that time. So classical segmentation techniques, like what we have seen so far, attempt to define the ROI in a precise manner, draw a boundary. And everything inside the boundary is a member. Everything outside is not a member. 0, 1. But tumors often don't have distinct boundaries, especially breast tumors related to cancer, malignant. They keep spreading, right? So the neighboring tissues are affected as the cancer spreads or metastasizes. So the density goes down slowly from inside the tumor to the outside. Where do you draw the line? So an alternative is to represent the tumor or mass regions by fuzzy sets, where there is a fuzzy membership between 0 and 1. A pixel belongs to a region with a probability or membership 0 to 1, not 0 or 1. So two segmentation methods were developed incorporating fuzzy concepts. The first method determines the boundary of a tumor or mass by region growing after pre-processing based on fuzzy sets. The second is a fuzzy region growing method. So one gives a boundary, the other gives a region. So pre-processing. So we know that a mass or tumor appears on a mammogram as a relatively dense region, denser than the other tissues. Calcifications are even denser. Tumors can contain calcifications within them. So malignant tumors in general are heterogeneous in density, but still they are denser than the surrounding tissues. And these could be characterized using local density, gradient, texture, and other measures. We'll see texture later. So you can compute a set of such local properties using blocks, or for the tumor, or maybe from somewhere you have this reference vector of these features, whatever the features be. And the feature could be just a gray level. Simple. So for each pixel there is a feature vector. And when you want to incorporate another pixel in the region, you get the feature vector for that pixel and take the distance between them and use that to define the membership. So given a feature vector, a pixel whose properties are similar to those represented by the feature vector of the mass could be assigned a high intensity. If not, the pixel intensity could be made low. Intensity now in the output is membership. At the end of this process, the pixels in and around the region of interest, the tumor, will be displayed according to their degree of similarity with respect to the features of the mass region of interest. So you define a fuzzy set by assigning to each element, let's say universal set, the whole set of everything, omega, a value representing its grade of membership in the fuzzy set. This grade corresponds to the degree with which the element is similar to or compatible with the concept represented by the fuzzy set. Some of the terminology is computer science terminology here. So this is the membership function that maps from omega to L, where L is a set that we have. So let's say the membership function has this range 0 to 1, and that facilitates easy analysis later, and that's the membership value. So you can call this as enhancement in the sense regions in the image or pixels in the image that do not belong to this mass or whatever it is you are defining will have low values. Those that are determined to be part of this set, fuzzy set, will have high value. And these values are between 0 and 1. And later on you can threshold or do something more. But in the initial step, you get this. The original image is mapped to a fuzzy set according to a membership function. It assigns a membership degree equal to 1 to those pixels that possess the same properties as the mass region of interest or the reference. It represents the degree of similarity between the features of the mass region and those of the pixel being considered, exhibits symmetry with respect to differences being positive or negative, and decreases monotonically from 1 to 0. So these are the requirements, and a commonly used membership function is like this. 1 over 1 plus beta, it is some factor that controls this function called the opening of the membership function. And this magnitude of a minus b is the difference between the feature vector of the mass of what you want to detect and the pixel being analyzed. In the simplest situation, this could be the seed value from where you're starting, where you know it is a mass, and the other one could be the current connected pixel, like region growing we did. But now there is another factor controlling this, and it is 1 over 1 plus that. You can even put a function here, some exponential function or something else. So the fuzzy membership degree will look like that for positive and negative differences between the feature vector of the RO and that of the pixel being considered. So if beta is large, the opening is narrow, this function will decay rapidly. If beta is small, then it's a wide function. So the output is between 0 and 1, membership. This is all the same as what I said. So here is an original mammogram, and you take, suppose the radiologist or somebody marks a pixel there and says, I know this pixel is in the mass or tumor. And from there you start the process and apply it to the whole image, whole mammogram. So we are showing a part of a mammogram, and this is the fuzzy membership. So this is 0 to 255 or whatever. In some cases we digitized using 10 bits. The scanner gave 12 bits, but it had some noise, so we cut it down to 10 bits. But this is 0 to 1. So now you say that some of these regions have very low membership. Regions within, or pixels within the tumor have high membership. Now you can do region growing on that rather than this. And you can get better results. So here is the result. This is a speculated malignant tumor. Pixel size is 62.5 micrometers. This is the result of fuzzy set based enhancement. So all of these have very low membership. This is enhanced. Contour, the white line is by region growing. The black line is the boundary drawn by the radiologist. There are some parts here that we are missing. The black line is drawn by the radiologist. The white is by this method. So this is, sorry, that is a different one. D is fuzzy region growing. We will go to that later. This is the current result. Here, fuzzy region growing parameters, we will see that later on. Okay, so that is the current result. We'll come back to the other part later. So fuzzy segmentation based upon region growing is another. The 4 connected neighboring pixels that are above the threshold are labeled as 0, and neighbors of the pixels labeled as 0 are inspected, and the procedure is continued. So it's the region growing now on this result. So that part is the same as what is before, so no need to go through that. So here is an example with a test image, a circle with noise. And using different seed pixels. This is the original with Gaussian noise added. Seed pixel 6060, which is somewhere, and threshold 0.82 on the fuzzy region growing method. This is the contour we obtained. A different seed pixel 6860, we got that. And 3 different seed pixels, we get similar results, not exactly the same, based on fuzzy region growing in spite of so much noise. So here is another mass example. This is after fuzzy pre-processing, and the region growing. Black drawn by the radiologist, white by this method. We will get to that later on. Okay. So the concept is that if you pre-process this image using fuzzy set membership, then you get a better result in region growing. Excuse me. We tested this with a few mammograms, 47 mammograms, and there are some results. I won't go through the details. You could read that later on. We defined a measure of fuzziness to compare the results obtained by the segmentation with the contours drawn by the radiologist. The method uses fuzzy fusion. We will talk about fuzzy fusion again later, where we say the result of fusion was evaluated by computing this measure. Fx, x is the result of aggregation, gamma p is the degree of membership of the pixel p. The denominator normalizes the measure with respect to the area of the result of fusion. And 0 here represents perfect agreement. Unity indicates no intersection between the two inputs. So the values of the measure of fuzziness were used to analyze the accuracy of the results, and we got results in that range with mean and standard deviation being that. But that is something you could read later if you want to get the fine details of analysis. We also did pattern classification using these results. So we wanted to derive a measure, morphological erosion, with we will talk about morphological image processing later, with a structuring element equal to 25% of the shorter dimension of the rectangle containing the contour was applied. And the core of the region was separated from the boundary. And we computed this parameter we call DCV from the fuzzy set pre-processed image as the difference between the coefficient of variation, which is sigma over mu, of the entire region to that of its core. The high value of DCV represents an inhomogeneous ROI. That is, the density variation is substantial, which could be indicative of a malignant tumor. The probability of malignancy based on this coefficient was computed using logistic regression. And we found a cut point for classification. So we got a specificity of 1, but the sensitivity was a little low, of the order of 0.64. So the probability of malignancy, 0 to 1, this negative doesn't apply, that is just for plotting, was computed as this sort of S-shaped curve. And you have to put some threshold somewhere. And then you can cut the samples into benign and malignant, as I mentioned earlier. We also developed another method for fuzzy region growing, where the membership that is assigned is between 0 and 1, and then of that we avoid finding a boundary. We're not interested in finding a boundary, and we have done more work on this, where we argue that it's not necessary to get the exact boundary of a malignant tumor because no such boundary can be defined or may exist. A radiologist will not draw. Here it's been done only for reference. But in general, the boundary of a malignant tumor is not clearly defined, so why bother finding it? Instead, if you can find a fuzzy region that approximates the tumor with high membership inside and low membership in the boundary, and at some point it stops, we can compute other features independent of the boundary using this fuzzy membership. So for that, we said we will grow fuzzy regions. So here, an adaptive similarity criterion is used for region growing, with the mean and standard deviation of the pixels in the region being grown as control parameters. Some idea similar to the other region growing criteria I described earlier, where the reference values were changed as a running mean and so on. And here we are using these as control parameters. The region is represented by a fuzzy set to preserve the transition information from the inside of the tumor to the outside. That is where the critical information lies. So the algorithm starts with a seed region. You can mark a region or 1 pixel, it's up to you. Somebody has to do that first, or an algorithm has to do that. Either give a pixel or simply a region. And from that you compute some statistics, mean and standard deviation. and then keep adding 8 connected pixels appending to the region. The homogeneity of the region that is developing by region growing is evaluated by calculating the mean, mu, standard deviation sigma, coefficient of variation sigma over mu. The coefficient of variation, one has to be careful. It is defined for distributions for which the mean is not 0. Otherwise, you have a problem here. Divide by 0. But this is of density, intensity, positive valued images, so mu is always greater than 0. And then we defined delta mu max, delta CV max, beta as control parameters. Delta mu max specifies the maximum allowed difference between the value of the pixel being analyzed for inclusion and the mean of the region already grown, that is growing. Delta CV max indicates the desired degree of homogeneity between 2 subregions or a pixel coming in and the region being grown. Beta is the opening of the membership function that we saw earlier. And let P be the pixel being analyzed and IP be the value of that pixel P. So region growing that we saw earlier, we compare the current pixel value to the seed. So here we are comparing IP to mu, the mean of the region being grown. If it is less than or equal to delta mu max, that is one condition. If it is not satisfied, the pixel is rejected. If it is satisfied, P is temporarily added to the subregion and mu nu and sigma nu are calculated. And then you ask the question, how much is the deviation if I include this pixel in the region? CV, this is before and after inclusion, coefficient of variation. If that is less than delta CV max, which is a parameter, then P must be added as accepted and mu and sigma must be updated. So mu nu, sigma nu are kept. If it is not satisfied, P is added with the label you accept it because it passed the first condition, but we are not going to change the statistics of the region. So small deviations will be allowed, pixel values will change. So you keep them if they meet that condition. If they meet this condition, you allow that pixel to change the statistics of the region. Otherwise, you still keep the pixel in the region, but you don't change its statistics. So the second step analyzes the distortion that this new pixel could cause to the statistics, and by putting that condition, we maintain some stability. Otherwise, the region could keep growing. So this parameter works as a filter that avoids the possibility that the mean and standard deviation suffer undesirable modification. So the algorithm processes pixels in expanding concentric squares. So many of the region growing algorithms can give different results depending upon how you scan the image for inclusion of pixels. Do you keep going in this direction or in that direction? Here we took squares. We looked for immediate connectivity around the pixels, the pixel that we are including. So this also provides some stability. The scanning process or procedure is also a factor to be considered, and some scanning procedures may lead to regions going away in some direction and not in other directions. So you don't want a preferential direction in region growing, and the expansion in concentric squares was found to be appropriate here. The membership function I said, and that is the rest I have already said. So the membership function characteristics are these. The membership degree of the seed pixel must be equal to 1. Of a pixel labeled as rejected must be 0. Membership function must be independent of the seed pixel or region. So you are computing some parameters and feature vectors. The membership degree must represent the proximity between the pixel labeled as accepted or accepted with restriction and the mean of the resulting region. Perhaps proximity is not spatial proximity, but in terms of the properties, grayscale, texture, whatever you have. Here we only use grayscale. The function must be symmetric, I showed that earlier. The function must decrease monotonically, and The membership function, we gave a different definition here. It's mean of seed region plus standard deviation of seed region minus mu, and this B is delta mu max. These are two parameters of the function. I'll show in a moment. The value of the pixel P is mapped to the fuzzy membership degree if the pixel value minus the mu is less than this threshold tau, defined by that A. Then this gamma P is equal to 1. The membership is 1. Otherwise, the membership 0 if it is outside the range B. Otherwise, in between A and B, you have this fuzzy function. This is the same fuzzy function I mentioned earlier. So it looks like this. There is this limit A, below which you give a full membership function, and after A up to B, you give this fuzzy membership, and after that, beyond B, you reject. So the noisy disk image I showed earlier, now we are not getting a contour. Previously, we applied the fuzzy membership function, fuzzy pre-processing step rather, which is also a membership function, and then we did a region growing and obtained the boundary. Here, there is no boundary, no contour, I should say, and all pixels are assigned a membership, but the membership outside is 0. Inside is most of them have white membership, full membership. There are some in between values, they are hard to see, and some may not have a membership because the noise is too high, membership being close to 0 because of noise. But most of them are included with high membership. So depending on the seed pixel, we get 3 different results for the same input image, but they are all very similar. So now we say the region has been identified. We haven't drawn a boundary, because drawing a boundary on a malignant tumor is difficult. But from this, we can compute other types of features. So we tested with 47 mammograms and came up with some parameters that were suitable. To assess the result by pattern classification, we defined a fuzzy ribbon. The fuzzy ribbon is a connected region whose pixels possess membership degree less than unity and separate the tumor from the background. So around the periphery of a malignant tumor, we expect many pixels to have low membership to the tumor, but not 0. The central core of the tumor is not important in the classification process. The membership is all high, but that distinction doesn't matter between benign masses and malignant tumors. In a benign mass also you have a central core where the membership is high. Let me show the pictures and then I'll explain that. So this is the fuzzy ribbon. I don't know why this came in color. Some strange things happened in the printing process. I didn't have any color, but when the book was printed, it changed to that. Or the EPS file somehow acquired this color. But there's no color, it's just grayscale. You can see we have removed the central core portion of the tumor. And this is the fuzzy ribbon around the periphery where the membership is less than 1. And we can put some limits. If it is less than 0 point something, then you don't keep it. This is for a benign mass. What we have observed may not be obvious in this case, that in the case of malignant tumors, there are more pixels in the fuzzy ribbon that are fuzzy, meaning the membership values are low, than in the case of benign masses. There is a rapid transition from the mass to the outside. The ribbon is thinner and the values are not decaying as slowly as here. So we computed the probability of malignance based upon the coefficient of variation, that is sigma over mu, of the pixels in the fuzzy ribbon. So we put a cut point of 0.8, and 20 of the 25 malignant tumors and 20 of the 22 benign masses gave correct classification. So this is the computed curve for the probability of malignancy and CVFR, the coefficient of variation of the fuzzy ribbon. Ideally, you want that to be a step function. So any threshold will work, but you get this always. So that you have to find a cut point somewhere, and there will be some misclassification. The sharper the transition of this S-curve, the better. The other one was not as good. This has a slower transition. So this feature, DCV, is not very good. And the accuracy was not as good as this current one. This is better. But if you can design one that goes like a step function, that is even better. Okay? Take another little break. Any question? Okay. Now segmentation, as we have seen so far, region growing and so on, did not assume any particular shape or size of the objects. Give a seed pixel and say, okay, look for something similar and keep growing region, and whatever shape and size we get, that's a region. But there are some situations where the geometry of the object you want to detect is known, that it is circular or it has this particular shape. If you can parameterize that shape and represent that using a few parameters, you can create a parameter space of the shape and then apply that in a method known as the Huff transform. You can generalize that, it's called generalized Huff transform. So sometimes images may contain objects that may be represented in an analytical form, such as straight lines, circles, ellipses, and so on, parabolas. I'll show you examples. There may not be perfect circles and perfect parabolas. You won't get perfect circles, fine. But if the contour of that object approximates a circle, and you can fit a circle, and there are circles of different sizes, then you can detect them and characterize them. The edge of the pectoral muscle in mammograms, I have not shown that yet, is an almost straight line in the mediolateral oblique views of mammograms. I'll show detection of the pectoral muscle later. Benign calcifications and masses appear as almost circular, but I don't think we want to try that. I don't think one would want to try fitting circles, but they're approximately circular. Most cells in pathology specimens have circular elliptic boundaries. Some may have rectangular shapes, and they have different connotations. So you can fit circles and ellipses and rectangles and then categorize them. Parts of boundaries of malignant tumors may be represented using parabolas. I'll show that later. So the detection, modeling, and characterization of objects or parts of objects in this manner may be facilitated by prior knowledge of their shapes. There was a classic paper where the ribs were detected using parabolas in chest X-ray images. So there are situations where some parts may be approximated by certain mathematical functions for contours or closed loops. Some say this is not Huff but Ho, but I'm not sure if I should go. I have asked in England too, and nobody could give me a correct answer. Huff like rough, or is it Ho like dough? I don't know. I say Huff. So Huff proposed a method. This is a classic paper. Y equal to mx plus c. Use this representation for a straight line, and he proposed this method for the transform that is named after him. But after this, Duda and Hart changed that formulation. We will see that too. So y equal to mx plus c. This is the equation for a straight line. X and y are the space coordinates, m is the slope, c is the intercept of the line. The Huff domain, or what is called the parameter space, straight lines are characterized by MC, slope, intercept. In the XY space, that is the equation. Given one value for M and one value of C, there is only one line there. Given a line, it is determined by MC. Okay? So that's the graphical representation of the line, the slope. Here it is rho equal to x cos theta plus y sin theta. Otherwise it's y equal to mx plus c. X coordinate, y coordinates, the intercept of the y-axis c. There's a problem with the y equal to mx plus c. C could be anything. The slope is, depending on how you define it, it is limited. But C, if it is a line that goes there or nearly perpendicular to the x-axis, then what do you do? Whereas rho equal to x cos theta plus y sin theta. Rho is the distance of this perpendicular to the line from the origin. And theta is its angle. Theta can go from 0 to 180, not 360, 180 is enough. And then the distance, it depends on how you define it. I'll show some definitions later. Rho is this distance. If it comes this side, you can say rho is negative, just mathematical notation. Otherwise, if you want rho to be only positive, then theta should go 0 to 360. With this definition, rho and theta are bounded. Y equal to mx plus c has the problem that c is unbounded. So this is a better representation. This is what Duda and Hart used in their paper after Huff's paper. So both M and C have unbounded, depending on how you define that, ranges, and then it is better to use this formulation. The origin is another thing. Where is the origin in your image? Do you want it in the middle of the image, or do you want the top left corner? So depending on that, the formulation will change a bit and the limits will change. So let's look at the detection of straight lines. So you have a bunch of pixels x and y and n going 0 to n minus 1, number of pixels along the line, but it could be broken. You don't need all the pixels along the line. If you have one here, one there, and one more there, that's enough. Two points would be enough, but when you detect an edge or a line in an image, you will get a few pixels, and some of them may be a little off. It is assumed that the image has been binarized such that the pixels that belong to the line have a value of 1 and everything else is set to 0. It is advantageous if the line is 1 pixel thick. Otherwise, within a thick line, you could have multiple lines. So which line do you want is the question. So try to skeletonize the line that you have detected. So the line is only 1 pixel thick. Otherwise, the problem is, if you have that is fine. But if you have a line that is thick, within this you can draw so many lines connecting all these pixels. You can even draw lines like that. So you get a bit of a mess in the Huff space. And then you find the best and still work. So the normal parameters of the line are rho naught, theta naught. All pixels along the line satisfying this x n cos theta naught, y n sin theta naught. That will form the line. So for a given pixel x and y n, what happens? This equation defines a sinusoidal curve in the rho theta space. Rho naught, theta naught are parameters in the rho of one point in the rho theta space. X and y n are pixels, these pixel coordinates that you have somehow segmented, detected, marked. And for a given value of x and y n, then you have an equation in rho naught and theta naught. That will form a sinusoidal curve in the rho theta space. And all the curves for these n pixels along that line should intersect at that point rho naught, theta naught. Many sinusoidal curves will intersect at that point. I'll show examples soon. A point xy in the xy space corresponds to a sinusoidal curve in the rho theta space. Using that same equation, a point in the rho theta space corresponds to a single straight line in the xy space. Points lying on the same straight line in the xy space correspond to different curves through a common point of intersection in the parameter space. Points lying on the same curve in the parameter space correspond to lines through a common point in the xy space. So this is the set of properties of the Hubble space. For lines and any contours you want to analyze, any shape you want to analyze. The sinusoidal is for this straight line equation. So the procedure is discretize the rho theta space. Rho and theta, rho could be from, if you take the origin to be the center of the image, it is the half diagonal of the image. 0 to half diagonal. Theta, then depends on how you define rho. Theta could be 0 to 2 pi, 360 degrees, or 0 to 180 if you allow rho to be positive and negative. Rho is distance. So it cannot be negative, but if you say if it is below the x-axis it is negative, then you can use the same equation. I did it that way. So discretize, for the sake of programming, the image is already discretized. Call that rho k, k going 0 to k minus 1, theta l, l going 0 to l minus 1. The bins are called accumulator cells because you keep adding values to that, incrementing by 1. And you put some limits on rho and theta so that you can define an array. 2D, in this case a 2D array. For each point in the given image that has a value of 1, a pixel that you have detected and marked, increment by 1 each accumulator cell in the rho theta space that satisfies that equation. Rho equal to xn cos theta plus yn sin theta. Equality, but satisfy plus minus something. If it is closed, you say, yes, I'll take the closest bin. So exact equality needs to be translated to some acceptance rule. The coordinates of the point of intersection of all the curves in the parameter space will provide parameters of the line, assuming there is one line. If there are multiple peaks, then you must detect all of them and get all of those lines in the image. If several lines exist, there will be need to search for all possible points of intersection. Points of intersection means that value will be large. So search for all local peaks and get all of those lines and then say which line do I want. Maybe only one, or maybe you will keep some of them, throw some of them out. A threshold may be applied to detect only lines that have a certain minimum length. Number of pixels will be, which will be the value of that peak in the Hubble space. How many points satisfy that equation for that line? A point is a pixel. How many pixels lie on that line? So all cells in the parameter space that have counts above the threshold may be taken to represent straight lines or pieces of straight lines with the corresponding rho theta values and numbers of pixels. Sometimes a line may be broken, you get multiple segments. So here's an example. I had quite a bit of fun doing all these in MATLAB. Until 1996 or 7, I didn't know of MATLAB. I don't know when did MATLAB start, about that time, 90 or 95 or something. I used to teach image processing before that and signal processing, and I wrote old Fortran programs. Nobody knows Fortran anymore, I suppose. You know, okay. You use Fortran? Anybody else Fortran?
77.
Oh, what?
Fortran 77. Yeah.
You still use?
My reader.
Okay. In my engineering course, 1971 to 76, my final year in electronics and communication in Mandayam, University of Mysore, PES college was 1976. We had a computer programming course, no computer, not even a calculator in the whole town and college. And we studied programming. We wrote an exam, writing programs, not knowing where it'll go. And anyway, we got marks and passed. Only after going to the Indian of Science, we could punch cards and stick the cards in the computer. Also punch tape Anybody has seen punched tape? Paper tape readers? No. Punched cards? How many of you have seen punched cards? Museum. No, have you used? Yeah, I will also be in a museum soon. Okay. So I created these using MATLAB, but before that, when I started teaching image processing, I had my own Fortran programs, and I would give the executable code to my students and say, run this with this parameter. And there were no monitors to display. And we would print on paper using superposed printing, an algorithm given in the book by Gonzalez and Wins. And then monitors came up, and anyway. This was easier, but I had to learn. My students taught me MATLAB to begin with. So here's this line I made up, and every pixel here gives a sinusoidal curve here. This is the image space, this is the half space. So there are many pixels here and many sinusoidal curves, the cos theta plus sin theta, something that we saw. They all intersect here. So that gives you the rho and theta. Rho equal to 20. Rho theta is 20, 30 degrees. I defined the origin in the middle, x-axis plus minus 50. 0, minus 50 plus 50, minus 50 plus 50. And half transform, log of 1 plus accumulator, horizontal axis 0 to 180 degrees, vertical axis 0 here, minus 75 to plus 75. I define distances below the x-axis as negative, just for programming convenience. So that, you find that peak, you got the parameters of the line. 2 lines. So there are 2 sets of the sinusoids. One intersecting there, another intersecting there. So you get the parameters 20, 30 degrees and minus 50, 60 degrees. Okay. But this is minus because it is below the x-axis, the distance, rho. Yeah. Detection of circles. The equation for a circle is x minus a square plus y minus b square is c square. Now we have 3 parameters. xy input space is only 2, but the parameters for the circle are a, b for the center and c for the radius. So a circle is represented by a single point in the 3D space, ABC. One point in that space, ABC, is a circle in the xy space. The points along the perimeter of a circle xy space describe a right circular cone in the ABC space. So if x and y are fixed, then you get an equation in ABC. What will that define? We'll define a right circular cone. I'll show you that. The algorithm for detection for straight lines is just extended the same, find peaks, but now in a 3D space, ABC. So here's a circle on a discrete grid, 30 by 30, a radius of 10 pixels, centered at 15, 15. So this is the half space in slices. Each image is of size 30 by 30. That is the size of the original image. So what you're doing essentially is for every pixel here, you draw a circle there of that radius. They're all a bunch of circles, but they're not intersecting. And here you're drawing those circles. But as you come here, they intersect at a common point. And then they diverge again. So here we have C going 1 to 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, 36. So the peak is for C equal to 10. 6, 7, 8, 9, 10. That is the global maximum in this space of 30 by 30 by 36. So you find the global maximum, so that's the best circle I have. If you only have one circle. If you want to find more circles, then you take the next peak and the next peak and the next peak and check if they are good for you. So the circle is detected. That is the global maximum, and by design we know that corresponds to C equal to 10 pixels radius. And that is our circle. So this is that collagen fiber image. So I thresholded that and got their boundaries. And what I did for display purposes is I got the boundaries in white, turned them to black, and overlaid with 10 times the C equal to 5 plane and C equal to 7 plane. C is the radius of the circle in the half space, like this. The half space looks like this, but now it is more complicated. I'll show you that. And I overlaid the half space, and inside each of these circles you will see a bright spot indicating that is a circle matching the C equal to 5 plane. C equal to 7 plane, you don't have a bright spot in that. You have a bright spot somewhere there, somewhere there. So wherever there is a bright spot, you say there is a circle. Is that correct? You compare with this. These are not perfect circles, but still there will be some match. A circle, if a full circle may have 50 points, but you may have 40 pixels, so you get that much of the corresponding peak. So if you detect this in the half space, then that's a good circle detection for that. Another one, and so on. I'll show you another example. These are the half space slices. No peaks, and multiple peaks appear here, and then there are not many peaks. So C equal to 1 to 12. And we used 5 and 7 there. 5 is this, 7 is this. So there are some peaks here you can see. No such peaks there. And there are multiple peaks, multiple circles of different radius values. You want to detect all of them. And then you can go back. For all the peaks you detect here, go back and put that value, mark that position and check what is there. Is that a collagen fiber or not? Originally it is dark. So you check, is it dark? Or some range of Hounsfield unit or whatever it is, the parameter. If it satisfies the conditions, take it. Sometimes some gaps here could also be fitted with circles. So if it is white inside around the dot that you detected, you say, no, that cannot be what I want. So post-processing helps you reject some of these. So the half space just gives you these points of high probability of occurrence, let's say, of a circle. I'll give you another application later. Maybe if I do in one of my seminars, if I am able to do the image processing for ophthalmology, I'll show you that. Here's another example. The collagen fibers, big and small edges. This is superimposed with 10 times the C equal to 13 plane. No, which one? Yeah, C equal to 13, C equal to 20. 13, you have 3 circles. The other one, you have 3 there. These two, maybe that. You see half, it is a broken circle, but still getting some output. And that's the half space for various values of the radius. Almost done. We'll stop here. This I did only to superimpose and give a visual display. In an algorithm, you wouldn't do that. You just detect peaks here, local maxima, and then check conditions and accept or reject. Okay, we'll take a break here. It's 10 to...
It's not yet ready, so...
Not yet ready. Okay. 10 more minutes? Okay. There are methods to improve an initial detection. You get an initial region and you say, well, it's not good. How can I fix it? So the user may wish to impose conditions, smoothness of the contour. And you want it to be authenticated by an expert like a radiologist. So they may modify the contour, and there are some graphical tools available to push and pull individual pixels and fit some spline functions or some other functions. So polygonal and parabolic models, you could put a model to this and say, well, there are some minor variations that I don't care for. That could be artifactual due to the imaging conditions, noise, or the accuracy of the algorithm. So I'll smooth over that and fit some curve, maybe a circle, maybe a parabola, whatever is suitable for the application. I'll show you some examples later. Polygonal and parabolic models, B-spline and Bezier curves. So those could be built into, the B-spline and Bezier curves could be built into a tool, a graphical tool, where you show the obtained result and let the user add just some pixels. So this pixel is too far and pull it out, and it maintains continuity with the rest. Active contour models or snakes, we will see that later. The live wire was a method proposed by Udupa and his colleagues, where they said you mark some points and then the contour that is obtained is required to include those points in the process. So they guide the detection process to say you must include these points and pull certain points towards the points that they give as input or reference. Fusion of multiple results of segmentation is what I'll show you later on. You get a contour from here, you get a region from there, something else from here. Do you take each one of them, or could you put them all together and get a better result? We will see that later. Detection of the spinal canal is something I'll show you, but we will get to that again later on.